Welcome to this session. Today in this session, to solve the numerical, we'll have to understand the concept of modular ratio and stress and strain in a composite member connected rigidly together parallelly. So let us first understand what modular ratio means. So modular ratio is signified by a symbol M, and it is the ratio of modulus of elasticity of two different materials. So modulus of elasticity is signified with symbol E, and it is the ratio of two different materials of modulus of elasticity. So E1 divided by E2. So this is modular ratio, and E1 here is modulus of elasticity of material 1. Similarly, E2 here is modulus of elasticity of material 2. So this is modular ratio. Now coming to the second concept, stress and strain in composite member connected rigidly together. Now in this case, let us consider a composite member made out of two different materials. Okay, composite member here means the best example of composite member can be a RCC structures. So I'm taking this column here, and this column here will be made out of steel and concrete, right? Concrete. So steel and concrete. So steel plus concrete is making this column here, right? See this RCC structure here. So this RCC structure here is a composite material, which means that it is made out of two different material. So similarly, let us consider a composite material of length L, and they are connected rigidly at its base. Okay, it is connected rigidly at its base, and these two composite material are made out of two different material. Let this be material 1 and material 2, and they are carrying a compressive load from above, compressive load P. Now when this load will be transferred among these two member, and they will be carrying it as P1 and P2. It will be distributed. So now if I want to find the total load of this composite material here, so total load P will be equal to P1 plus P2, right? Now from the relation stress sigma equals to force by area, I can find force from this relationship as P equals to sigma into area, right? Now if I want to find P in P1 in here, so my P1 here will be equal to sigma 1 area 1. Similarly, if I want to find P2 here, P2 will be equal to sigma 2 A2. Now substituting the value of P1 and P2 in this equation here, we will be getting P will be equal to sigma 1 A1 plus sigma 2 A2. So we will get this equation here, right? Now always remember that in a composite material, if there is increase or decrease in length of this composite material, there will be, if this P1 is increasing, its length is increasing, the length of P2 will also increase. If the length of P1 is decreasing, the length of P2 will also decrease. So they will have same increase or decrease in length in a composite material. Let us consider this in this case here. So considering that strain strain E, right? What will we get from the relation again of modulus of elasticity E is equal to stress by strain, right? So from this equation, if you find strain E will be equal to, if we cross multiply it, we will get strain E into E equals to sigma, right? Now from here, strain E will be equal to sigma by E. We get this relationship, right? Now I want to find strain in this first material, and the strain in this first material E1 will be equal to sigma 1 divided by is modulus of elasticity E1. Similarly, E2 in this second composite material will be sigma 2 E2. Now we know that the strain in both this composite material will be equal. So strain in first material will be equal to strain in second material, right? So my strain in first material is sigma 1 by E1 is equal to sigma 2 by E2. Now from here I want to find sigma 1. So if we cross multiply it, we will get sigma 1 E2 equals to sigma 2 E1, right? Now I want to find sigma 1. So my sigma 1 will be equal to E1 divided by E2 into sigma 2. We get this relation from here, right? If I want to find sigma 1. Now, what is E1 and E2? E1 here is modulus of elasticity of material 1 divided by modulus of elasticity of material 2. Now, this is the E1 divided by E2 is a modular ratio. So, we can further make it as sigma 1 equals to modular ratio M into sigma 2. So, this relation we will be using in solving the numerical. We will be using this relation, and then we can also use this relation to, if modular ratio is not given, then if one modulus of elasticity is given and the other modulus of elasticity of the second material is not given, if we have to find E2, then we will have to use this relation here to find either E1 or E2. And next we will be using this relation here. So please remember the relations that we are gonna use, and next we will be using you have to know what modular ratio is and its expression of modular ratio. So let us solve the numerical. Question 1. RCC column 300 mm into 300 mm is reinforced with 4 bars of 16 mm diameter. Determine the stresses induced in steel and concrete if it is subjected to axial load of 450 kilonewton. Modular ratio is given 13.33. So what is given here? A steel RCC column is given. RCC column is given, and its dimension is given as 300 mm into 300 mm, right? So it is RCC column, and it says reinforced with 4 bars of 16 mm dia. So there are 4 bars, 1, 2, and 3, and 4 bars. So these are 4 bars, and their dia is 4 bars of 16 mm dia, right? So this is a column, and it is made out of steel and concrete. Now we have to find stresses induced in steel and stresses induced in column, right? So what is given? Given here is P. Axial load P is given equal to 450 kilonewton, which will be equal to 450 into 10 raised to power 3 Newton. Then next, modular ratio is given M. Now here modular ratio M will be equal to modulus of elasticity of steel. Modulus of elasticity of steel divided by modulus of elasticity of concrete will be, it is given equal to 13.33. Okay, because here in the question it says stress induced in steel first and then concrete. So we have steel by concrete. Okay, then next we can find the area of this concrete. Area of concrete A can be equal to 300 into 300, which will be coming equal to 9 into 10 raised to power 4 mm square. So this is the area of the whole of, I'm sorry, not concrete, this is area of column. Area of column A will be equal to this much. Now we want to find area of steel. We can find area of steel from this given diameter here, right? So area of steel, AS will be equal to, we find it as pi by 4 d square, and the diameter given here is 16 mm. So into 16 square, right? And we have 4 bars, so into 4. So this is for 1, and if we multiply it with 4, we get area for whole of the steel that is used in this column. So we get, let us solve. I'll just cancel it here. This will get cancelled here. So we have pi into 16 square. So pi into 16 square will give you 804.25. 804.25 mm square. Now we have found the area of the column and area of the steel. Now we can find area of the concrete now. To find area of concrete, AC, we just need to deduct from the total area of the column. Area of column minus area of steel. So if you do this, we get area of concrete, right? So area of column, total area of column was 9 into 10 raised to power 4 minus 804.25. So let us see how much we get. This will be coming equal to 9 into 10 raised to power 4 minus answer. So this is coming 89,195.75. 89,195.75 mm square. So this is the area of concrete. Now we have found the area of concrete. To find stresses induced in steel and concrete. Now to find stresses induced in steel and concrete. So remember the formula that we have found. Sigma 1 is equals to modular ratio into sigma 2. So we will be using this in this case here. So here sigma 1 here is stress induced in steel is equal to modular ratio given was 13.33, and sigma 2 here is stress induced in concrete. So we have this here. We get this value here. Now we need to find sigma S and sigma C. How do we find? We find it from the relation P equals to sigma 1 area 1 plus sigma 2 area 2. From this relation we will find the value of sigma 1 and sigma 2. Now here sigma 1 is stress induced in steel, and it will be area of steel plus stress induced in concrete into area of concrete. So how much is load given? Load given was 450 kilonewton. So 450 into 10 raised to power 3 Newton equals to sigma S. Sigma S is equals to 13.33 sigma C. So I have 13.33 sigma C into what is the area of steel? Area of steel is equal to 804.25. We have 804.25, right? Plus what is sigma C? We don't know sigma C, so let this be as sigma C only. Okay, into area of concrete, how much was it? 89,195.75, right? So it was 0.75. So let us solve this one. If I solve this one, keeping this as it is, 450 into 10 raised to power 3 equals to, so let me solve this one here, 13.33 into 804.25. This will give me 10,720.65. 10,720.65. Now this sigma C will remain as it is, so it will be sigma C plus this will be 89,195.75 sigma C. Now we can add these two terms because they are like terms, they have the same unknown variable, so we can add these two up. So adding these two up, we will get 450 into 10 raised to power 3 will be equal to plus 89,195.75 will give me 99,916.4. 99,916.4 and sigma C. So now from here we can find the value of sigma C. Sigma C will be equal to 450 into 10 raised to power 3 divided by 99,916.4. So this will be coming equal to 450 into 10 raised to power 3 divided by the answer that we have. So it is coming 4.5. So stress in concrete is coming 4.5 Newton per mm square, right? Now we have found the value of sigma C. Now from this relation, sigma S equals to 13.33 sigma C. So we can substitute the value of sigma C here. So it will be coming equal to 13.33 into 4.5. So this will be coming equal to into 13.33. So this is coming equal to 60 Newton per mm square. So this is the stress induced in steel and this is the stress induced in concrete. So I hope this numerical is clear. Let us solve second numerical. A reinforced concrete of square section 400 mm into 400 mm carries 4 mile steel rod at each corner. So we have a square section, okay, so this square section's dimension is given equal to 400 mm into 400 mm, right, and it carries 4 mile steel, 1, 2, 3 and 4, and its diameter is given equal to, so these are 4 bars of 30 mm dia, right. Each is subjected to an axial thrust. The same stress for the corner is limited to 6 Newton per mm square. So the stress is given 6 Newton per mm square, and the ratio of modulus of elasticity m. Modulus of elasticity of steel to concrete. So modulus of elasticity of steel to concrete is given equal to 18. So find the stress developed in steel and total. We need to find stress developed in steel, right, and total load P, we need to find P. Then next, load shared by steel and concrete. Load shared by steel and load shared by concrete. Load shared by concrete. The stress that is given here is the stress induced due to concrete. So stress induced due to concrete, sigma C, right? Now let us find the area. Let us start by finding the area of concrete section. Concrete section A will be equal to 400 into 400. It will be coming equal to 16 into 10 raised to power 4 mm square, right? So next let us find area of steel. Area of steel AS will be equal to, there are 4 bars into pi by 4 and its diameter is equal to 30 square. So we have cancel these two. We have pi into 30 square. So we get 2827.4. 2827.4 mm square. So we have area of steel also. Now let us find area of concrete. Area of concrete AC will be equal to area of concrete section minus area of steel, which will be equal to 16 into 10 raised to power 4 minus area of steel 2827.4. This will be coming equal to 16 into 10 raised to power 4 minus its answer. So if I just do this, it is coming 157.17 into 10 raised to power 3. 157.17 into 10 raised to power 3 mm square. So this is the area of concrete. Now from the relation sigma 1 equals to modular ratio into sigma 2. So here sigma 1 is steel and modular ratio into sigma C. So from here sigma S here is equal to modular ratio given is 18, right? So 18 into sigma c given is 6, right? So 18 into 6, we get 18 into 6, 108. 108 Newton per mm square, right? Now we have found the stress induced in steel. Now next we have to find the total load. To find total load, P will be equal to sigma stress in steel into area of steel plus stress in concrete into area of concrete, right? So let us find one by one. First, let us find load in steel, right? So total load shared by steel will be equal to sigma s as, which will be equal to sigma s is 108 into area of steel is 2827.4. 2827.4, which will be equal to into 27.4. So this is coming equal to 305.36. 305.36 into 10 raised to power 3 Newton, right? So next we have sigma force shared by the concrete, which will be sigma c into area of concrete. So sigma c given was 6 into area of concrete came out to be 157.17. 157.17 into 10 raised to power 3. So this will be equal to 6 into 157.17 into 10 raised to power 3. So this is equal to 943.02. 943.02 into 10 raised to power 3 Newton. So I have this. Now the total load P will be equal to 305.36 into 10 raised to power 3 plus 943.02 into 10 raised to power 3. So this will be equal to plus 305.36 into 10 raised to power 3. So this will be coming equal to 1.25 into 10 raised to power 6. 1.25 into 10 raised to power 6 Newton. So I have the force induced, the total load shared, the total load of this concrete is coming equal to 1.25 into 10 raised to power 6. So I hope this numerical is also clear.